Okay, hello. Today I just want to talk to you guys real quick about the special pattern for factoring. When we're factoring quadratics, a lot of times we can just, make a double bubble and we're all good. When we are factoring some special polynomials, though, there are some patterns that can help us out. The pattern that I'm going to look at today with you is the pattern for the sum and difference of cubes. First of all, this happens when we have two perfect cubes that we're either adding or subtracting. And so first, I want to make sure that we can recognize what the perfect cubes are, okay? 1 cubed is, of course, 1. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. Hopefully you're familiar with those already. But here's some other perfect cubes that will hopefully become more and more familiar to you as we go through these factoring problems. 6 cubed is 216. 7 cubed is 343. 8 cubed is 512. 9 cubed is 729. And of course, 10 cubed is 1,000. So it's important that when we see these values, that we recognize these as perfect cubes, and that could help us use this factoring pattern. So what is the special factoring pattern? Well, the special factoring pattern is to factor when you have two perfect cubes that we're adding or subtracting. Now, of course, first what we're going to do is think about what our what the cube roots are in each one. So we're going to take the cube root of a cubed, which is a, and the cube root of b cubed, which is b, and that's going to be one of my factors. But let me tell you what we don't do. This is not equal to a plus b cubed. Let me review what happens when you have a plus b cubed. Remember when we studied Pascal's triangle, we said that if we have the quantity a plus b cubed, that we would end up with a cubed plus 3a squared b plus 3ab squared plus b cubed. Notice it's not a cubed plus b cubed. So we don't just want to factor that as a plus b cubed because it's just not correct. Let me tell you the second part of the double bubble. The second part is going to have a squared minus ab plus b squared, okay? And then the nice thing about this is that even though often it ends up being a quadratic, that can't be factored anymore. You're done. Then if it's a cubed minus b cubed, we'll start with the quantity a minus b, and then we'll have a squared plus ab plus b squared, okay? And a mnemonic device to kind of think about what happens in that second factor is SOPs. S-O-P-S. And what SOPs, I don't want to say what it stands for, but it can kind of, what it can kind of help you remember is that it represents that you're going to square, then take the opposite of the sign that was in the original problem. You're going to take the product of the perfect cubes, and then once again, we're going to square. Okay, so that's what I mean by SOPs in that second one. The first one's pretty easy. We just used the cube roots, and then we use the square. We take the opposite sign of what we originally had. We take the product of the two cube roots, and then we square once again. Okay, and again, one thing I do want to note is that this cannot be factored any further. Okay, don't waste your time. Okay, so to do this, it's important that we first, again, identify any perfect cubes that we have in the problem. Okay, so let's look at that in example 2. In example 2, what we have is we have w cubed minus 27. And hopefully you recognize this as a perfect cube and another perfect cube. And as we start this, I'm going to request that you write what the cube roots are before we begin. Well, the cube root of w cubed is w, and the cube root of 27 is 3. So that means that we're going to use w and 3 as our a and b. So this follows the second pattern. So we're going to use w minus 3 as our first factor. And then we have the factor that uses steps. We're going to square w, take the opposite sign, so we're going to add, take the product of w and 3, which we don't write as w3, we'll write as 3w, and now square the 3, and we get 9. And that's it. So the cool thing is that when you use this pattern, like afterwards, you're like done, okay? Let's look at letter B, 27x cubed plus 125. So again, I'm going to request that we start by figuring out what the cube roots are. What are we cubing to make 27x cubed? Not 27x. That would mean that we have 27 multiplied by itself 3 times. But to make 27x cubed, that means that we're really cubing 3x. To make 125, we're really cubing 5. And now that we have that, we can utilize the pattern. We have our cube roots. So our first factor is going to be 3x plus 5 because we had addition in our original problem. Then we need to square 3x. Now remember, we're not just squaring x, we're squaring 3x. So that gives us 9x squared. Let's take the opposite sign. The product of 3x and 5 would be 15x. And now we square 5 to make 25. And that's it. And I know that trinomial, that quadratic trinomial looks factorable. I promise you it's not. Okay. Now let's look at letter C. Well, in letter C, we've got negative 2d to the 5th plus 250d squared. Not perfect cubes. But what are we supposed to do to start any factoring problem? GCF. I noticed that the first term is negative, so I'm for sure going to take out a negative. I can take out a negative 2, and I can take out d squared from each one. And that leaves me with d cubed, and then minus 125. Oh my goodness, look what popped up. 2 perfect cubes. So let's rewrite this using the cube roots. Of course, the cube root of d cubed is d, so I put that in the parentheses. The cube root of 125 is 5. And now I can use the pattern. So I'm going to take d minus 5 for my first factor. Then I'm going to square d, take the opposite sign, the product of d and 5, so 5d, and then I need to square the 5. Now before I happy cloud, remember that I had a GCF of 2d squared. This isn't really, I'm not necessarily saying that this is equivalent. I mean, I guess I could move this down here, okay? But that was just a step for me to see what the perfect cube roots were, okay? But now that I've brought down the original GCF, here's my question. Let's do one more, letter D. 16b to the 5th plus 686b squared. Well, again, I can take out 2b squared. And that would leave me with 8b cubed plus 343. Now I know 8's a perfect cube. Oh, and look, 343 is a perfect cube too. So let's rewrite this using the cube roots. What are we cubing in each case? What are the cube roots? Because that's what we use in our pattern. Well, this is going to be 2b and 7. So that means that if I'm going to factor 2b cubed plus 7 cubed, that's sum of two cubes. I'm going to use 2b plus 7. I need to square all of 2b to get 4b squared. Take the opposite sign. The product of 2b and 7, remember product means multiplication, 2b times 7 would be 14b, and then square the 7, 49. Make sure I include my GCF in front, and there we have it, okay? So that's how we can factor the sum and difference of cubes.